It's a pleasure to have Lara Anderson as the next speaker, and she'll tell us about constraints in smooth heterotic compactifications. Please, Lara.
Thank you very much. And thank you to the organizers for a great conference. This is one of my very favorite conferences in the year. And I'm grateful that despite the pandemic and everything, we have a chance to still interact in this format. So thank you to all the organizers for making this possible. So today I'm going to be talking about constraints in smooth heterotic compactification. I'm going to touch on a number of sort of different features of 4D smooth heterotic compactifications. And I'm going to look in most depth at a paper from earlier this year, which was done in collaboration with James Gray at Virginia Tech, Magdalena Larfors, Matthew McGill, and Robin Schneider in Uppsala. So thank you to all those collaborators. So the nice thing, again, about this conference is that the motivation slide is largely unnecessary in this audience. As we all know, string theory is a powerful extension of quantum gravity, but we need to actually extract interesting 4D physics from that. One avenue within the subject of string compactifications is, can we produce interesting four-dimensional models that might be useful for particle physics, for cosmology, et cetera? And that really bifurcates into two problems. The first one is that in any given corner of the string landscape, as we've heard many talks about this week, actually pushing your control of the effective theory to the necessary level of detail is extremely hard. So the technical skill set to control a string compactification, to really write down the full details of that theory and try and understand under what circumstances it will look like the ones you're after, are extremely difficult. And then the other problem is, of course, that there are many choices, many corners of string theory to explore, and many different choices of compactification geometry that you might employ. And one needs to, as much as possible, understand what sort of broad scale patterns, constraints, and predictions one can extract from that geometry without doing detailed calculations. And of course, the whole swampland program that we've heard much about this week is very much delving into those ideas. So today I want to sort of look at a combination of those two effects, both an advance in technical control in one corner of string compactifications, and also what one can say about some general structure within 4D smooth heterotic string compactifications. Because I saw from the poll earlier this week that roughly 30% of participants have never been to a string pheno conference before, I do want to just define the background geometry of heterotic string in a bit of detail. So to begin with, I'm going to consider a 10-dimensional E8 cross E8 heterotic string theory, and I want to dimensionally reduce this to 4 dimensions with n equals 1 supersymmetry by choosing a complex SU3 structure background. For this talk, I'm going to focus on a Calabi-Yau threefold and the data of gauge field vevs over that background geometry to reduce myself to a 4-dimensional theory. Two bundles, V1 and V2, embedded in each E8 factor, whose structure groups are a subgroup of E8. Compactifying on that pair, XV will lead to an n equals 1 supersymmetric theory in 4D if certain conditions are satisfied, which I'll talk more about in a second. While the presence of the vector bundle over the Calabi-Yau will break E8 to a smaller group. So if, for example, I have a vector bundle with structure group G, then I will end up with a commutant in E8 H, where H will be my low energy gut group. So as examples that have been much explored in literature, for example, if I choose a bundle with SUN structure group where N is 3, 4, 5, that can lead to the famous 4D guts E6, SO10, or SU5. And all of the matter in moduli are highly constrained in that reduction. All matter comes from the adjoint of E8 in 10 dimensions. The decomposition of the 248 specifies what massless charged and uncharged states you can have in 4D. So following up on that, in heterotic models, the 4D particle spectra, what type of matter, what charges you can have, of course, are constrained by the decomposition of the 248. And how many are counted by bundle-valued cohomology groups. As an example, if I have an E6 theory in 4 dimensions, the number of 27 and 27 bars, which are the E6 charge matter, are counted by bundle-valued cohomology in the fundamental and anti-fundamental of the bundle, and singlets, which would be counted in the adjoint. Likewise, I will, of course, have singlets in the theory, lots of them, unfortunately, for the problem of moduli stabilization, Kähler moduli, complex structure, and bundle moduli in general. One more bit of background. In addition, there'll be a whole bunch of constraints on sort of the structure, equations of motion that I must satisfy, and the topology of the theory. So for example, the topology of the bundle is constrained. C1 of the bundle has to be 0 mod 2. And in fact, a little bit stronger than that, the net C1 of all reducible components must be exactly 0. Mod 2 is only relevant when you have multiple pieces. Anomaly cancellation tells you that if you fix the base Calabi-Yau geometry, then the C2 of the bundle is actually bounded. It is forced to be differ from C2 of the tangent bundle only by an effective curve. And to satisfy supersymmetry, I need not only a Calabi-Yau solution or SU3 structure solution more generally for the background manifold, I also need that the vector bundle has to satisfy the Hermitian-Mills equations over the Calabi-Yau background, i.e. that the vector bundle is Mumford stable. Furthermore, I have this 4D gut theory. I can then attempt to break that gut down to something resembling, for example, the standard model. I could employ fluxes to do that, or familiar two-step symmetry breaking, where the bundle itself only breaks to the gut group, as I mentioned on the previous slide, and Wilson lines could be added to break further. These would be discrete Wilson lines in the case of Calabi-Yau threefolds, and you could, for example, break SU5 directly to the standard model gauge group. For this latter possibility, you need a non-simply connected Calabi-Yau in order to have the available discrete Wilson lines to do this breaking. And that you can obtain if you have a simply connected Calabi-Yau that admits a freely acting discrete automorphism. You can quotient by it to produce a non-simply connected one. And you can classify which bundles can exist on this non-simply connected object by considering equivariant structures on the cover. Okay. So that's a bit of general background about 4D heterotic compactifications. Now, let me try and motivate the context of the work I want to talk about today, which is it's within this particular corner of string theory. Smooth heterotic compactifications are very nice in that they are under quite strong perturbative control. A lot is understood about how to engineer the matter spectrum and consistent geometries of the type you're interested in. But we really want to understand what can be said in general about the 4D effective physics before one goes to the great labor of constructing many detailed models. So obvious features that you can say, as I've already mentioned and is very well understood, of course, the gauge group is bounded within the context of smooth compactifications by the E8 cross E8 parent group in 10 dimensions. The charge matter spectrum, what representation content you have is all bounded because of the decomposition of the 248. This means that you're going to have very different structures, for example, in the 4D gut theories, and that there is no adjoint Higgs. So you can't do sort of normal gut breaking as 4D theorists would. You're going to need to employ other techniques. Here are a few less obvious constraints that one can immediately say about the theory. Some things you can say is that, in fact, the ways that you can break symmetry are highly constrained. So there was interest a few years ago, my collaborators and I, Andre Constantine, Sungju Lee, and Andre Lucas, were interested in whether there were alternatives to Wilson line breaking, discrete Wilson line breaking in smooth heterotic compactifications. And we explored so-called hypercharge flux breaking, which is essentially a choice of a gauge bundle that directly breaks to standard model gauge group. This, for example, would be very similar in spirit to the types of constructions that Patrick was just talking about in an F-theory dual. So this would be something where generically for that choice of topology, you have exactly standard model symmetry. What we showed with is that if you try and do this, this for smooth Calabi-Yau threefolds is actually incompatible with the exact charge matter spectrum of the standard model, i.e. exactly 3 families of quarks and leptons was incompatible with any hypercharge breaking independent of a Calabi-Yau background. So this tells you that in fact, Wilson line breaking is the only way to go if you would like to do standard model type building in a smooth Calabi-Yau. Other examples, you can argue that in fact, from an understanding of geometry, there has to be a finite number of generations of charged chiral matter. So for example, it has been understood in the mathematics literature that for slope stable bundles with a fixed C2, excuse me, yeah, I said that right. For slope stable bundles with a fixed second Chern class, the possible values of the third Chern class, which governs the chiral index in the heterotic theory, must be finite. I.e. for a fixed C2, there's a finite number of values of C3. Now, if you understand that the C2 as it appears is bounded by anomaly cancellation in the heterotic theory by the base Calabi-Yau that you chose, then that tells you that if you tell me we've picked a Calabi-Yau base, then the number of topological types of bundles that can sit over it is finite. And in fact, that tells you that there must be a finite number of generations in your theory. So there is no, theory with 10 to the 5 billion generations necessarily. We don't know exactly what those bounds are, but this is something that we'd very much like to understand from a swampland field theory perspective, how those bounds appear in an n=1 theory. They're also, because of the fact that the discrete symmetries that arise through quotienting of Calabi-Yaus and equivariant structures appear to be very crucial in terms of obtaining standard model-like spectra in the heterotic backgrounds. What symmetries can arise on smooth Calabi-Yaos are very constrained. These are understood to be bounded. Order 64 discrete groups is the highest that has been found so far. And again, the bound is non-constructive at the moment, but these will lead to residual discrete symmetries, which can play a big role in the effective physics as well. So this is simply to give a sort of brief sampler that there are many aspects of the structure of these 4D theories that you would expect from 4D field theory to be unconstrained, which in a heterotic context are constrained. And one can ask whether that is either useful or problematic for the type of effective physics one wants to build. So in today's talk, I want to take a deeper dive into yet another constraint that appears to arise quite ubiquitously in heterotic backgrounds. And these are constraints to do with the trilinear couplings of the theory. Like Sakura, if some of you are having deja vu from my string talk, I will reassure you I'm going to sort of go at this in a bit more depth in a different angle than I did at strings. So hopefully it won't be super boring. But let me give a little bit of background about these perturbative trilinear couplings. So if I have a Calabi-Yau manifold and a gauge bundle over it, the trilinear couplings in the superpotential are defined around that perturbative background. So we imagine that we have a gauge field, which is defined as some background gauge field. That's our underlying bundle. And then the connection on that gauge field can fluctuate away from that background choice. And that fluctuation is going to produce 4D matter fields. So the scalar fields phi that are appearing in your 4D theory are being controlled by these bundle deformations by harmonic one forms that are parameterizing the fluctuation of the connection over the Calabi-Yau. So for these matter fields, then the trilinear superpotential couplings, which would look like coupling of three fields, lambda ijk, this has a simple integral form that has been well understood for the last 25 years, where you take your harmonic forms, wedge them together with a holomorphic top form, and you integrate over your Calabi-Yau threefold. Two things that should be stressed. I have this tilde here on purpose. So two things we don't know. The actual normalization of these fields in a given background is dependent on the matter field Kähler potential, for which you need to know the actual connection and metric on the background bundle and Calabi-Yau geometry, which, as we know, is hard to come by, and just recently with machine learning we're working on, but in general is unknown analytically. And we expect that these numbers are actually functions of the complex structure in bundle moduli, and extracting that moduli dependence can be quite challenging. Now, why do we care about these perturbative couplings? Of course, there are non-perturbative effects we have to consider. If we consider, actual phenomenological backgrounds, we need to break supersymmetry. We're going to run and regrow various couplings down to lower energies. There's a bunch of calculations that have to be done, but if you can't control this basic perturbative structure, it's going to be much harder to specify anything else. So we're interested in very particular textures and hierarchies. For example, in the standard model, we understand that the top quark is comparatively very heavy. So that could be something that you would expect to see in a structure like this. You want to forbid certain terms, for example, the SUSY mu problem. You want to forbid a mass term allowed by gauge symmetry. You might be interested in rapid proton decay operators. There's a bunch of things that you would like to control within this structure. So the goal of my collaborators and I in sort of studying these trilinear couplings again, which is a subject that people have thought about in many contexts over the last 20 years. So what things do we want to come at from a fresh angle? In general, in order to understand these heterotic effective theories, we need very good tools for actually computing these couplings in masses, preferably long-term in a moduli-dependent and fully normalized way. We want to predict general structure, again, from the point of view of not diving deep into computing a ton of really costly things for one geometry, only to find out this isn't the model you're interested in. How do we sort of see general structure before you even begin the calculation? The first observation that you can make from particular examples, multiple particular examples that have appeared in the literature already, is that heterotic theories can exhibit topological vanishings. These are vanishing couplings that must be due to the structure of the geometric background rather than gauge invariance of the theory. So a goal for my collaborators and I was trying to understand, for starters, what geometric effects in a heterotic compactification can lead to topological vanishings. How are these different effects different or related? How generic are they? And are they actually not due to symmetries? So for example, could there be hidden symmetries of the theory that are forcing these topological vanishings? And could they be useful for pheno? So just to give a simple example of that latter point, which has been around in the heterotic literature for a long time, I mentioned the heavy top quark. So you could imagine a situation for model building where you, in the perturbative theory, force all couplings except those involving one quark to be zero perturbatively, you regrow the rest non-perturbatively, and then you've introduced a nice hierarchy of masses into your theory. So there's a lot of ideas along this line that have been well explored by various people. Okay, so first pass, how to actually compute these things. So the very first examples in the literature were ones that arose from the so-called standard embedding, where the gauge bundle was chosen to be the holomorphic tangent bundle of the Calabi-Yau threefold. In this context, you can appeal to mirror symmetry, in which these couplings may be simply intersection numbers of the mirror. This was done by Strominger, Candelas, and others. Or also something that was observed very early in heterotic model building in the late 80s, early 90s, is that you can take an algebraic geometric approach, which is to map this integral that I described of harmonic forms over the manifold into a so-called cut product or unita product in cohomology. So you can take the bundle valued one forms, these are not the harmonic representatives, simply the D-bar closed ones, and you can actually write down a product in this cohomology, which can give you a number which is interesting up to overall scale, i.e. you can see structure about these couplings using this approach. So given an algebraic representation of a bundle valued cohomology, here I described what it would be for a 27 cubed coupling in an E6 four-dimensional theory. You can turn this into a problem of polynomial multiplication. Okay, so alternatively to that, a few years ago, a very interesting paper by Blesniak et al., including Andre Lucas and Philip Candelas, tried to approach these couplings more from the point of view directly of the integral. So they took a differential geometry approach, and they were interested in the context, specifically in that work of line bundle models in the heterotic context that were defined on a Calabi-Yau that is built as a complete intersection in some simple ambient space. They considered ambient spaces that were simple products of projective spaces. And if, for example, this is defined by a single polynomial hypersurface, and you additionally assume that the bundles and forms descend from nice bundles and one forms defined on the ambient space, then you can write down this integral in terms of this object delta 2p, which is a delta function current, which is related to the defining equation in the following way. Since you understand that the holomorphic form wedge with dp is related to this sort of normal form to the Calabi-Yau within a given ambient space, they were able to very nicely write down sort of a closed form expression for this trilinear coupling. And they're able to describe this in terms of objects with the hats, which are not necessarily closed on the ambient space, but restricted closed forms on the Calabi-Yau. However, in the case of simple ambient spaces, this allows you to see very easy structure about where this integral has support in the ambient space. As a really simple example, if you have, small dimensional like P1 factors in an ambient space, depending on the number of legs of these objects in given directions, you can read off vanishings in terms of that ambient space description very quickly. So this was a really neat formalism. As I'll talk more about later, this also allowed them to extract some moduli dependence of these couplings. So some questions that we set out to tackle: how are the differential and algebraic approaches related? Is there a more general framework for studying these things? And can calculations be streamlined? So in the algebraic approach that I, for example, had worked with a lot previously, you end up with these giant grids of sequences, which if anybody who's ever worked on these calculations, before you even get to the difficult basis of doing a Grosvenor basis calculation, you have to sequence chase a giant mess. You have to feed all this into a computer. You have to do a Grosvenor basis. It's a pain in the butt. So we were looking for ways to improve this situation, and we observed that certain tools from homological algebra can improve the situation. I'm not going to go into detail what these are. You can see our paper for the types of tools that we employed, but I can say that there are really remarkable speedups for the particular problem that we wanted to do by using nice understanding of the underlying geometric structures that come with these triple products. So as one of my collaborators said when we learned this mathematics, I feel like I know Kung Fu. We were able to really speed up these calculations. What we did was to prove a number of theorems about the structure of these vanishing theorems, and I'm only going to give a brief flavor of one here. So basically, the way that the homological algebra enters is, instead of thinking as a manifold embedded into a certain ambient space, we think about a given resolution of a bundle as some simple objects, these are my FIs, which are specifying the bundle I'm actually interested in the Calabi-Yau. As one example, this could be a description of simple objects on an ambient space, like I just described in the differential geometry approach, or it could be something entirely intrinsic to the Calabi-Yau, just a set of simple sheaves or bundles which are specifying the ultimate gauge field that you're interested in. What we showed is that in terms of any such description of this type, which is extremely broad, you can define a notion of type for elements of the bundle-valued cohomology, which is where they descend from in forms that are related to objects in this sequence. The details of this are not super important. Again, you can see our paper for this particular talk, but we classify elements of H1b by type if they descend from Hi of Fi minus 1. We say they are type I, And then subject to certain vanishing conditions on these defining objects, we can argue that all Yukawa couplings must vanish of certain types. As a special case of that, we're able to reproduce the work of Bosniak et al., which was previously not at all obvious from the sort of algebraic geometry approach. Using a causal resolution, we can read off the same vanishing structure that they observed for general bundles, and we can apply it much more broadly to other resolutions, either in terms of ambient spaces or other data. So
Lara, you have 5 more minutes.
Great, thank you. So the basic idea of the differential geometry approach, as I just outlined it, is that you're using information about an ambient space to get information about a coupling on X. Just 2 quick points that I found very useful in this. It turns out that embedding one manifold, you can choose different embedding ambient spaces to describe the same Calabi-Yau, unsurprisingly. So as an example here, I give an SU3 bundle, which has 2 different sort of descriptions as a sum of line bundles on 2 different descriptions of a complete intersection manifold that happen to give you the same Calabi-Yau. What we find is that with these different ambient space descriptions, we can actually see different vanishings using these theorems. Now, the idea here is that any information you can get from any description is valuable. So the fact that these can differ means that if you have multiple descriptions of the same manifold, you could use those multiple descriptions to extract more information. Another very similar effect is even if you have one manifold, a bundle on the Calabi-Yau can actually be lifted to different objects on the ambient space. So the idea is really simple. You can have sheaves on the ambient space, which have singularities, which make them not good gauge fields, not good bundles. But they can actually restrict to bundles on the Calabi-Yau if the singular loci of the sheaf misses the Calabi-Yau hypersurface. So you can uplift one bundle to multiple different objects in the same ambient space. Here I gave an example of 2 different objects for the same complete intersection Calabi-Yau, where the singularities of the sheaf miss the Calabi-Yau. And in this case, again, these different descriptions of the object on an ambient space, either as a bundle, either as a sheaf, can give you different constraints in the trilinear couplings. Since I'm short on time, I'm probably going to skip this. You can ask how much of this moves to higher order in the superpotential. I'm talking about trilinear couplings. The answer is basically all of it. So higher order structure is Kuranishi maps. Perturbatively, you can use the same tools to start going higher and higher. I'm going to skip that in the interest of time. And let me just, as the last point I want to make before I run out of time, there were different sort of classes of topological vanishings that had been observed in particular examples in the heterotic theory in the literature in different, chosen compactifications in the past. And we were interested in whether we could sort of use our framework to describe all of these more systematically, and the answer is more or less yes. So the 3 classes are the ones I've detailed so far. Descriptions of the Calabi-Yau as an ambient space can lead to constraints on the couplings. You can also use descriptions of the Calabi-Yau as a fibration, which have been explored by various groups in literature in the past. It's clear you're going to have constraints on the couplings, and you can obtain constraints due to the fact that the vector bundles need not be stable everywhere within their Kähler cone, so-called stability wall structure. And what we find is that more or less the same tools can be used to describe all these different effects. One question you can ask is, given these different types of effects, must all these different descriptions agree in terms of where you're going to get constraints? And as we saw, even for 2 different ambient spaces or 2 different uplifts, you're getting different information. The answer is all of these different effects can in principle give you different constraints. So many examples exist where you can use an ambient space description and an elliptic fibration, or an ambient space description and a stability wall. And what you find is, in general, all of these are giving you different information about the couplings. What that means is that there is a ton of constraints hitting these couplings from the theory, and all available information can help you specify it. Of course, all these different descriptions or all these different windows are just describing the same theory. So if something is 0 in one description, it's going to be 0 in all the others, and you can, obtain that more or less easily from these different descriptions. I should say that in switching between these different viewpoints, like an elliptic fibration and an ambient space, of course, there is basis changes that happen there, and you have to be very careful that the zeros you're seeing are actually significant under that basis change. We did that counting very carefully and find that indeed they are. Just as one last comment, and then I will finish. On the subject of fibrations, you can also see, just like different ambient spaces can give you different constraints, it has been understood for Calabi-Yau threefolds that in fact, almost all the Calabi-Yaus that we have built to date within the Kreutzer-Skarka database within complete intersections appear to admit fibrations, genus 1 fibrations quite generically. And in general, they do not admit just one. We've seen examples with order 10s or order 100s, in one case, an actual infinite number of fibrations. And each of these distinct fibrations can induce topological vanishings. So in this context as well, you're really going to constrain these couplings. So heterotic couplings are generically highly constrained. So since I'm out of time, let me just try and put this all into context and say as a concluding remark, why should anyone care? So the idea that trilinear couplings could be zero in heterotic theories has previously been observed in particular models, and there were tools for calculating them in sort of one geometry. Our new work adds to this discussion in two ways. First, we've generalized quite robustly a framework with which to analyze these vanishing conditions using a description of resolutions of bundles in homological algebra. We can analyze when and why these vanishings occur quite generically from many different geometric aspects of the background. And we can demonstrate through lots of angles that these vanishings are surprisingly generic. These constraints appear to be very ubiquitous. That may be useful for model building, or that may be deadly, depending on how much you can control and what you're after. You can phrase all such constraints in a common language. And of course, there are many open questions. Can you see similar sorts of geometric constraints on higher order and non-perturbative contributions? I had to skip over this, but higher order, the answer is probably yes. Non-perturbative, less clear, though there's also interesting structure there. You can ask what the consequences of this are for dual theories, for example, heterotic F-theory duality. And it is still an open question to us whether some of these might have some sort of hidden symmetry origin. For example, the recent work of Vafa, Palti, and Weigand, which we're looking at, an infinite number of couplings vanishing. Does that imply that there has to be a sort of symmetry, hidden symmetry origin for that vanishing? This is not quite the same as the context they were looking at, but it feels similar in spirit in some ways, that many of these things are very constrained, and it would be nice to see a deeper structure for that. So with that, I will conclude. Thank you very much.
Thank you, Lara, for this beautiful talk. Are there any questions? Yes, Patrick.
Yeah, I maybe one detail that you probably explained and I just didn't fully understand at the time. So if for given two different geometric instructions with different sets of topological constraints, say you study the first of the two constructions and you find some set of topological constraints, do the set of constraints from the second construction also remain valid for the first one? Is that the idea?
Absolutely, yeah. So that's a really good point, and I probably didn't say that quite as clearly as I should have. So you have many different descriptions of the same geometry, the same physics. So the idea is you want to use all these different windows to try and constrain the theory, and there's only one of them. The subtlety in that is, of course, that you might be describing your fields in different bases in these different descriptions. And of course, you can diagonalize matrices, right? So you can set a bunch of things to zero using basis changes. So you have to be careful, like if I see a bunch of zeros here and then I move it to a different basis, like which ones were just explainable by a coordinate change. And we tried to do that counting very carefully, and we can show that these different descriptions differ by things that you cannot account for by coordinate changes. They're not inconsistent. If you were to calculate them in sort of one context, you would find like this one simply told you that something was zero. In this description, you would have to do a really long calculation to show it's zero, but it would still be zero.
I see.
So yeah, the information is all true. There's just one theory. And you have to be careful about how you conclude that when you're switching bases, but we tried to do that.
I see. So in principle, all of the information is in principle visible given a single geometric construction, but it may be very difficult to access, it sounds like.
Full control. Yep.
Yeah, I see. Okay, thank you.
Alon?
Yeah, thank you, Lara, for a nice talk. So I assume you have space-time supersymmetry in all your constructions. How much your conclusion depend on this fact?
So for Fino, you're exactly right. I mean, the question of the actual, I'm talking about, the top mass, right? But that is only a meaningful discussion after I've broken supersymmetry. So you're absolutely right that stuff can regrow. You've got to understand how that regrows and at what scale, and you got to do the whole running and break supersymmetry, stabilize the moduli. So this is a very preliminary stage. I am not claiming that I have used this effect for Fino or that there aren't other effects that are going to mess up the type of structure you're aiming for. But as I mentioned before, I think in the context of building these theories, this is sort of the simplest perturbative contribution. So before you deal with supersymmetry breaking, you've got to control this, and then you got to worry about what happens with everything else. And there are things I could say about that, but yeah, I would say the main reason that we have not pushed this all the way yet is that we do not have any vacua that are fully stabilized in a supersymmetric solution, or at least close enough that you can then try and add something like gaugino condensation in the hidden sector to break it. So we're still missing some ingredients in supersymmetry breaking and moduli stabilization.
Thank you.
Okay. If there are no other questions, then let's thank Lara again. And of course, there's the Slack channel, so if anyone has follow-ups,